In this video, we will explore a new data structure called heap. This video assumes that you are familiar with the terminologies of a binary tree. If not, in the cards and in the description, I have linked an article. Check it out and you are set. First, we will look at the working of heap. Then we will discover the operations which can be implemented for heaps. Then we will look at the code. And finally, we will be looking at the advantages and disadvantages of heaps. So, without any further ado, let's get into it. Heap is a special tree-based data structure where all the levels of the trees are completely filled, except the lowest level nodes, which are filled from as left as possible. Generally, there are two types of heaps, min heap and max heap. In min heap, the value of the root node is smaller than all its child nodes, and the same follows to the left and the right subtree. So, in min heap, the minimum element is always, you guessed it, the root node. Max heap is contrary to min heap. The value of the root node is greater than all its child nodes, and the same thing follows to the left and the right subtree. Here, the maximum element is always the root node. So, in min heap, we can instantly find the minimum element, and in max heap, we can instantly find the maximum element. In this video, we will be talking in terms of min heap. So, when I say heap, I mean min heap. Max heap is just the opposite of min heap. Let's see how to implement this structure in terms of code. To implement a heap data structure, we just simply define a structure called heap or min heap. This structure contains two attributes, node and current size. Node is an array which has a size of the elements you want to insert into the heap plus 1 because the array should be a one indexed or one base array. The second attribute, current size, represents the index of the last element which has been inserted. The current size is really helpful to find out whether the heap data structure is full or empty. The operations supported by heap are heapify. Heapify is the process where a normal array is converted into a heap data structure. The elements will be arranged such that the minimum element is the root of the tree. Let's look heapify operation in greater depth with an example. We have an array of 5 elements, 8, 5, 1, 3 and 4. We apply heapify to the array to convert the array into a heap. It results in the formation of heap 1, 4, 3, 8, 5. Now, what's this? I said that the array is converted into a heap, but here we see the array is as it is. Only the elements are shifted to some random positions. What's going on? If you know about the trees, then you know that each element's left child is 2 times I, and each element's right child is 2 times I plus 1, where I is the index of the element in the array. Let's see, is it true? The left child of the index first element, that is 4, is 2 times 1 is 2. The element at index 2 is 3. Something is wrong. It fails the main property of min heap. 3 is smaller than 4. It cannot be its child. We are missing something. Can you tell me what is wrong? Comment it down. I'm waiting. Okay. Yes, if we start our array at index 1, we get the correct results. Now, let's see what is the left child of the second indexed element, 4. So, 2 times 2 is 4, and the element at index 4 is 8, and yes, it holds the property. Now, what is its right child? 2 times 2 plus 1 is 5, and the element at index 5 is 5. Yes, it holds the property. Lastly, the left child of 0 indexed element. Wait, you are not paying attention. The array is 1 indexed. Pay attention. The left child of index 1 element 1 is 2 times 1, that is 2. And element at index 2 is 4. Yes, this holds the property. Using this knowledge, let's plot the data structure as a tree. Now some of you might feel comfortable. Here, the minimum element 1 is at the root. Its children are 4 and 3. You can calculate it. Children of 4 is 8 and 5. 3 has no children. Similarly, 8 and 5 has no children. Always fill the left subtree first, then we move on to the right subtree. To summarize, heap is a one-based or indexed data structure. That is, element starts at index 1. To find the left child of a node, just multiply its index with 2. To find the right child of a node, just multiply its index with 2 and add 1. To find the parent of a node, just divide its index by 2. Let's see how the heapify left child and parent functions are implemented in the code. We have already declared the structure min heap. To implement heapify operation, we require some helper function. The first helper function is the parent function, which takes the index of an element and checks if the index is equal to 1, meaning if the current element is the root. If yes, it returns -1. If it's not the root node, then it returns parent of that element by dividing its index by 2. Then we have the left child function, which also takes index of an element and returns its left child by multiplying its index by 2. Then we have the initiate function, which takes a min heap structure and initiates its current size to 0. Then we have our heapify operation, which takes array and the size of the array n. In the heapify operation, it creates a new heap called heap. It then initiates that heap. Then we have a for loop which iterates over the array, and the heapify operation calls the insert function, which we will be looking at soon, which simply inserts the element in the array to the heap, maintaining the property of the min heap. Now you might ask, yes, this is easy, but how to place each element in the heap in the correct order? That's why we have the insertion operation. The insertion operation places an element in the heap such that it maintains the property of the heap. To do so, insertion places the elements to be inserted in the last position of the heap. Then it applies bubble up to that element. Now, what is bubble up? The operation of bubble up is simple. It checks if the current element is greater than its parent. If yes, bubble up stops. If not, bubble up swaps the current element with its parent element. Again, bubble up checks if the current element is less than its parent. If not, the procedure is repeated recursively. Let's look at insertion with an example. We have our earlier min heap. We want to insert 2 to the heap. Insertion inserts 2 to the last position in the heap. 2 becomes the child of the 3. Yes, 2 is inserted into the heap or min heap, but it does not satisfy the condition. The parent should be less than the children of the min heap. Here, 3 is greater than 2 and 3 is the parent of 2. It completely violates the condition of min heap. So, insertion applies bubble up to the element 2. Bubble up checks if 3 is less than 2, that is, whether the parent is less than its child. In this case, no, so it swaps 3 and 2. Again, bubble up checks if 1 is less than 2. Yes, so bubble up stops and hence insertion is complete. This is how insertion operation works. Let's see how insertion operation is implemented in terms of code. Similar to the heapify operation, we have already declared a structure min heap. The insert function takes arguments, a min heap structure and an element to be inserted x. The insert function checks if heap is full. If yes, it prints a warning saying priority queue overflow. If the heap is not full, then it increments current size by 1. The element to be inserted is placed in the last position of the heap. Then bubble up is called on that element. Now, what is bubble up? Bubble up takes 2 arguments, the main heap data structure and the index of the element to be bubbled up. It first checks if that element is an root element. If it's a root element, it returns. If not, it checks if its parent element is greater than the current element. If yes, it swaps the current element with its parent element. Then it calls bubble up to its parent index, and then this process recursively calls until the element is in its correct position. Now, what if we want to delete an element from the heap? No worries, we can easily implement it. The concept is to replace the deleting element with the last element of the heap. Then apply bubble down to that replaced element. Bubble down is an operation where if the current element is greater than its children, the current element is replaced with its smallest of the children's. This process is repeated until the element is in its correct position. Let's apply this to our previous example. We want to delete the element 4 from our min heap. Deletion operation would replace the last element 3 with the deleting element 4. Now, deletion would apply bubble up to the element 3. Bubble down checks if 3 is greater than that of its children 8 and 5. In this case, no, so bubble down stops. Let's delete the element 1 from the heap. Deletion operation would replace 5 with 1. Now bubble down is applied to 5. Bubble down checks whether 5 is greater than its children 3 and 2. Yes, so bubble down swaps 5 with its smallest child 2. Bubble down stops as 5 has no children. Yes, we have successfully deleted the root node and retained the property of our min heap. Let's see how deletion operation is implemented. We have already declared the structure min heap. The delete operation takes two arguments, min heap structure and the index of the element to be deleted. The delete operation first checks if the heap contains any element. If the heap does not contain any element, it prints a warning saying priority queue underflow. Else, if heap contains any element, it replaces the deleting element with the last element of the heap. Current size is decremented by 1 and bubble down is applied to the deleted index. Bubble down takes two arguments, min heap structure and the index of the element, the index to be bubble down. Bubble down has two variables, C and min index. C contains the left child of the current element and we assign minimum index to be the current element. Then we run for loop 2 times. In the first iteration, we check if the current element has a left child. If yes, it checks if left child is less than the current element. If yes, minimum index is updated to the left child index. Again, in the second iteration, it checks if the current element has a right child. If yes, it checks if right child is less than the current minimum index. If yes, the minimum index is updated to the index of the right child. After the for loop, we have a if condition which checks if minimum index is equal to the current element. If not, it swaps the current element with the minimum index element. And again, bubble down is applied on that minimum index element. Finally, the element would be in its correct position. Before we move to the next operation, if you find any value in this video, hit that like button. For more videos on DSA, hit the subscribe button. Let's move on. Heaps also support getMax and getMin function. By now, you can tell how to implement it. GetMax is for max heap and getMin is for min heap. We are talking about min heap. As you know, in min heap, the minimum element is always the root node. I think you do not need code for this operation. Now we have the extractMin and extractMax function. These two processes are very useful for the popular sorting algorithm called Heap Sort. ExtractMin operation is only available in min heap and extractMax is only available for max heap. If you do not know the reason, then rewatch the video. ExtractMin operation would return the minimum element and deletes the minimum element or the root element. Let's apply this to our previous example. In this heap, we want to apply the extractMin function. It returns 1, then it deletes 1. The delete operation would replace 1 with 3. Then delete operation would apply bubble down to 3. 3 bubble down to the place of element 2. 2 is our new root and the minimum element. Note that unlike getMin, extractMin deletes the minimum element or the root element from the heap. Let's look at how extractMin is implemented. Now we look at the heart of the heap sort, extractMin. We have already implemented the min heap structure. The extractMin function takes argument the min heap structure. In the extractMin function, we have a variable called min which contains the index of the minimum element. Then extractMin function checks if heap is empty. If heap is empty, it prints a warning saying priority queue underflow. If heap has some elements, min is updated to the root element. The root element is replaced by the last element of the heap. Current size is decremented by 1 and bubble down is applied to the root index. Minimum element is returned. Before we jump into the entire code, I recommend you to convert an array into heap and apply all the operations on a paper. Okay, I will give you the array. The array contains the elements 9, 7, 4, 6, 1, 3 and 5. Apply heapify to the array to make it a heap. Then insert 2 and 10 into the array. Then delete 9 and 1 from the array. Now what is the last element? Comment it down below. After solving this problem on a paper, you will have a solid understanding on the concept of heap. I hope you have solved it and commented down the last element of the heap. Now let's look at the entire code. Now we have glued all our operation into a single file, and now let's test it. I run the test file. We can see the array before Heapify operation, which we can clearly say that the minimum element is somewhere in the array. When we run Heapify operation, the minimum element comes to the first place. As you can see, in the whole array, 0 is our minimum element and 0 is our root node. And we can clearly say that Heapify operation works. Let's move to our parent and left child function. The parent is 0's, left child is 1 and right child is 2. Let's compare it with the Heapify output. Yes, 0's left child is 1 and right child is 2. 1's left child is 6, right child is 22. 2's left child is 4 and right child is 3. And 6 left child is 10 and it has no right child. Yep, our left child and parent function works. Let's move on to our insertion operation. We insert 5 to our heap and our heap becomes 0, 1, 2, 5, 22, 4, 3, 10, 6. Let's verify it whether it satisfies our min heap. 0. 0's left child is 1 and 2. 1's left child is 5 and 22. 2's left child is 4 and 3. It satisfies it. Let's insert -1 to our heap. We insert it and -1 is our root node and insertion works completely. Now let's add 30 to our heap and we can see we get a warning, priority queue overflow. Why do you think it occurs? Now let's look at our code and you can see that we have defined our structure to be a size of 10 and our structure contains 10 elements. When we insert 30 to our heap, the heap is already full, so we cannot insert any element. We can clearly say our insertion works. Now let's test our delete operation. Let's delete 1 from heap and you can see I have given the command delete heap, 5. Why do you think I have given 5? Remember, delete operation takes the structure and the index of the element to be deleted. Here 1 is at index 5, so I supplied 5 to it. And you can see the output -1, 0, 2, 5, 22, 4, 3, 10, 6. 1 is missing. And our heap is in terms of the properties of min heap. Now let's delete 4 from our heap. And you can see 4 is deleted from our heap. Hence, delete operation works and we can gladly say that our main operations are working. Now, let's try getMin function and we get -1. Let's try it again. -1. Why is that occurring? Note that getMin only prints the root element of the min heap. It never changes the root node. That's the property of extractMin. Let's move on to it. extractMin, it gives us -1. Now let's print out our heap. We can see -1 is missing from our heap. As I already said, extractMin always extracts the root node. That's it. All of our heap operations and heap is working as intended. Now I have a challenge for you. Write the max heap structure and implement the same operation and make it work. I dare you. The source code is in the description if required. The complexity of Heapify insertion and deletion operation is big O of log n. In min heap, the operation getMin and extractMin takes big O of 1 operations, and in max heap, the operations getMax and extractMax takes big O of 1 operations. Now, why to use heaps? Heap gives a fast access to the minimum or the maximum element depending upon the type of heap. Heaps are efficient for insertion and deletion operation. Heaps can be efficiently implemented as an array. Heaps are suitable for real-time applications. The disadvantages of heaps are they are not suitable for searching elements other than minimum or maximum elements, which would take a big O of n operation. We require an extra memory overhead to maintain the heap data structure. It is slower than other data structure like arrays and linked lists for non-priority queue operations. Finally, if you wanna be a master of heaps, then just implement max heap by your own. Max heap is just the opposite of min heap. Think about the working, implement it on a paper, then write it as code. If you are successful to do so, comment down.
I have mastered heaps. Congratulations and signing out.